All right, so we've reached level 2.6, which is called Building Functions and Mathematical Models. And I will have to say, this section is the shortest, but also the most challenging, and it's because we're dealing with story problems. And story problems, by far, has been something that's scared us since we've been in elementary school with math problems. Something about putting words to numbers doesn't click for us. But this is the purpose of math, because we want to be able to represent our world in terms of numbers. So we're going to take some of the function stuff that we've learned and apply it. So let's just jump right in. There's no new things that we're learning other than looking at some of these problems and seeing if we can analyze them. Okay, so let P be any point on the graph y equals x squared minus 1. So let's first draw our graph. X squared minus 1 is a parabola shifted down 1. That looks like this. I want to express the distance from any point to the origin. So this is my origin, and let's call some number p out here. I want to be able to find the distance from any point. So that point is x comma y. Okay, so this is like putting level 1 and level 2 together. What's the distance formula? The distance is the change in x squared plus the change in y squared. Okay, so that's not that bad. The change in x squared, well, this is 0, 0, so that would just be x minus 0 squared plus y minus 0 squared. So that's just the square root of x squared plus y squared. Well, we don't want to just leave it as y squared, and we know what y squared is. Y squared is my function to begin with, so I'm going to replace this y squared with x squared minus 1. So I have d equals the square root of x squared plus x squared minus 1 squared. Okay, that's a little trippy. I know that's going to throw some of us, but when I square this all out, this quantity squared, I'm left with square root of x squared plus x squared times x squared. Square the first. That's 2x, that is x to the fourth. Multiply the 2 and double it, so that's negative 2x squared plus 1. So if I add like terms, x squared and negative 2x squared, I get the square root of x to the fourth minus x squared plus 1. That's my distance formula. That's my function in terms of x. So let's just call that f of x. That wasn't that bad. B, what is the distance if x is 0? So what's the distance from the origin here? So we can just plug that in. The distance is the square root of 0 minus 0 plus 1, which is just the square root of 1, which is 1, which makes sense because the distance from the origin to this point right here is 1. How about C? What's the distance if x is equal to 1? Well, again, if we plug in 1, we're going to get the distance equals the square root of 1 to the fourth minus 1 squared plus 1. Well, these two just cancel out, and I'm left with square root of 1, which is 1 again. So once we've come up with this formula, it's not so bad. Okay, what about if it's the square root of 2 over 2? This is a little trickier because we have to remember our radicals. So that is the square root of 2 over 2 to the fourth minus the square root of 2 over 2 squared plus 1. Square root of 2 over 2 to the fourth. This is square root of 2 squared is just 2 squared again, so that's 4 over 2 to the fourth is 16 minus 2 over 4 plus 1. So if I do this, and that's all underneath the square root, I'm left with the square root of 3 over 4, and that's all underneath the square root sign, which we can simplify to be the square root of 3 all over 2. So lastly, and I'm just going to switch over to Desmos to graph this for you, we're going to look at this function and see if we can find the local minimum. So using Desmos to do example 1, part E, we first need to graph it. So let's open up Desmos. You can see that I already have the equation that we've generated for example 1. So I'm going to see what this graph looks like. Again, remember that we're looking from the origin to our function, and I want to see where this function has a local minimum. So we can see that if we look here, we have mirror images, but our distances, we only want to be positive. So if I zoom in here and I select this point, I can see that I have a minimum at 0.7071, comma 0.866. That's our minimum distance. If you need help using your TI Nspires, I'll gladly show you guys in class how to use these. So example 2, we're given this picture and it says a rectangle has one corner in quadrant 1 on the graph, another on the origin, a third on the positive y-axis. Express the area of the rectangle as a function of x. Okay, so we first have to remember how to find the area of a rectangle. Well, the area of a rectangle is base times height. So our base would be the x and our height would be the y. So x times y. Now, just like we did before, let's get that on screen. We have already y in terms of x, so I'm going to plug that in. So that is x times 25 minus x squared. And that is our area. We can distribute this out if we want to be exact. So we could say that's 25x minus x cubed. So now we have an area function, and let's just say that's in terms of x. That's all that parentheses means, a of x, area in terms of x. So if we're looking at B, and it's saying find the domain, well, we can look at this picture, and we're looking at the area here, right? The largest x value we can have is 5, because our x-intercept here is 5. We also see that we're bounded by the y-axis. So this is the furthest left we can be, and this number here is 0. So if we can put those two together, and we can see just from this picture, the farthest left we can be is 0, the farthest right I can be is 0, and I can't be either of those two, because if you had an x of 0, that doesn't, we don't have a rectangle then. It's going to be 0 to 5. Everything else will be on Desmos. So using Desmos for example 2, part D, and C and D, you can see that I typed in my equation for example 2, 25x minus x cubed. Now, I want to see what this graph looks like, so I'm just going to tap that to see what our graph looks like. That doesn't quite look what we found so far, so I want to restrict this because I know we found earlier our domain was from 0 to 5. So I'm going to look right there. So now, we got 0 to 5. I want to know what's the largest value I could get out. So if I tap my graph, this is the nice thing about Desmos, I can see that at 2.887, I get an area of 48.11. Again, if you need help using your graphing calculators for this, I'll show you how to use them, but it's a pretty straightforward thing. All right, example 3, last problem of level 2.6 and last problem of level 2 overall. This one's a little long and it's a little fun, so bear with me. So we have a children's playpen manufacturer makes a square model that can be opened at the corners and attached to the right angles of a wall. Okay. If each side is 3 feet in length, the open configuration doubles the available area in which the child can play from 9 square feet to 19 square feet. Suppose we place the hinges at the outer corners to allow them for the configuration here. So what we're doing is we're putting these hinges out here to see if we get a different area. So express the area of this figure in 62 as a function of that distance x between the parallel sides. Okay, so that's our first thing. How do we do this? First of all, the area function that we're going to try to find this whole thing is going to be the area of the rectangle plus the area of the triangle that this shape is formed. And I'm going to just draw this to the side. We have this triangle that's looking like this. This length is x. We have this length is h. And this length is 3. And this length is 3. So that gives us a right triangle, which I'm going to draw this right triangle in even further to make our point. This is our h. This is our 3. This is going to be x over 2. That's a property of isosceles triangles. Okay, so the area of the rectangle, that's the base times the height. That's base times height. Area of a triangle is 1/2 base times height. So here, area of the rectangle is 3x. We don't know what h is, but we can solve for h. So h would be h squared plus x over 2 squared equals 3 squared. So from there, if I subtract this quantity over, I get h squared equals x squared over 4. So 9 minus x squared over 4. Excuse me. So then if we take the square root of that, which first off we're going to get common denominators. So we get 36 minus x squared all over 4. Now we can take the square root of both sides. Distances are never negative, so we don't have to write plus or minus. We're going to be left with the square. We can't take the square root of the top, so 36 minus x squared over 2. Now, why did we do all of that? Well, we needed to find out what h is, because our base is x. So I have x over 2 times the square root 1/2. So yeah, x over 2, then this whole thing, 36 minus x squared all over 2. Okay, so we're almost done. I'm just going to write these two quantities together. That leaves me with the area as a function of x is equal to 3x plus x square root 36 minus x squared all over 4, because 2 times 2 is 4. So that gives us our area. We can find the domain of this function. Why? What's the only thing that restricts this? Well, first, we're talking about distances here, so distance can't be 0. But then also we want what's underneath the square root to be positive. So we say 36 minus x squared is greater than 0. So I can either factor this, or I can see wherever 36 is greater than 0. So if I solve this, I get x is between 6 and negative 6. Square root both sides gives me inequality. But I know that I can't be 0, so it takes that part off. So I only want numbers for x that are less than 6. So my domain would be 0 to 6. And that's B. For C, it says find the area if x equals 5. So we're going to plug 5 into this and see what we get. So A of 5 equals 3 times 5 plus 5 times the square root of 36 minus 5 squared all over 4. So that's 15 plus 5 square root 36 minus 25 over 4, which is 11. So that's 16 plus 5 square root 11 over 4. And if we really, really wanted to simplify this, 16 over 4 which would be 64 plus 5 root 11 all over 4, which is approximately 19.15 square feet. The last problem that we'll see is that we're going to graph this and see what it looks like, and then we're going to try and find the maximum of the area. So switching back to my graphing calculator for example 3, I want to see what the graph looks like and also figure out what's the largest area and what is the maximum area. So largest area and maximum area mean the exact same thing. So I'm first going to click on this to see what my graph looks like. You can also see we kind of have a similar window, but just to be sure, I know my domain is from 0 to 6, because that's what we found earlier. And once I see that, there's my graph. If I want to figure out where the maximum is, I can just touch my graph here, and then I get my point. There's my maximum, which you can't really see. So if I scroll over there, you can see that my maximum value, my maximum area, which is my output, is the 19.82. And that happens when x is about 5.584 feet. So that's how we kind of go about these with utilizing the graphs to kind of get some other information.